an idea, actually. Yeah.
Welcome back, everybody. I'm Nasser Kaloud. I'm going to be your chairman for the afternoon, and we will open the session with the talk of Donatella Cassetari. Donatella, the floor is yours.
Thank you very much. Good afternoon. Oh, is it too loud? Yeah. Oh, okay. Okay.
So I owe you a welcome from my side. Yes. Maybe tomorrow. Maybe. Okay. So on behalf of the Academy, just a short announcement. I have to, of course, welcome you from our side, from the Institute of Theology and Psychology, which is a department of our Academy. But also, please note that we have an issue with a water shortage. It's an issue that it's something that has to do with the local area. The good thing is right now from the municipality, even if it's 3 o'clock, they are here in order they're trying right now to solve it. So hopefully by the end of this session, the water will be back. We'll keep you updated and we'll try our best to solve this issue. Thank you so much for your understanding.
It's a very good point, even though that's probably not directly related, but Crete is experiencing an extreme drought right now, so limit the amount of water that you're using generally. So just as a little reminder.
I guess we can all go in the sea. Anyway. Okay, so good afternoon. And thanks the organizers for organizing such a conference and for giving me the opportunity to speak. This is my second time in Crete. I was here 10 years ago for FOMO in 2014. I have great memories of really good discussions. So I'm very happy to be back. Can I double check, is the volume okay? Because I can hear echo coming back, but does it sound good for you? Okay, good, so I can continue this way. So this talk is about prime factorization in holographic traps. I'd like to start by thanking the people who are working on this, so Renzo Testa, Daisy Matthews, and myself at the University of St. Andrews, together with Carrie Weidner, Massimo Ciani, Giuseppe Sardo, and Andrea Antoni. Andrea, Renzo, and Carrie are here at the conference, so you're very welcome to go and speak to them as well. So I'd like to start with the experimental setup, actually. In St. Andrews, we have worked for several years on what we call holographic optical traps. We use a spatial light modulator to define optical traps that are suitable for trapping ultra-cold atoms and bosons and condensates. So here is a schematic of the SLM. It is spatial light modulator. It receives a laser beam. And the SLM is a phase-only device. So each is made of pixels, and each pixel will impart a given interpretation onto the incoming laser beam, so that if you look at the output of that, we go in the far field of diffraction. Experimentally, you do that with the lens, and then we go into the focal plane of the lens. And here in the focal plane of the lens, we can create different intensity profiles. For instance, here we have a line of lights which could be used as a very elongated trap for atoms. So we spent a lot of time developing good algorithms to solve this problem. So this is an inverse problem. You start from the intensity profile that you want. So for instance, it looks like this. And you need to calculate backwards the phase profile that the SLM is part of the laser beams. So this is an inverse problem. And the one way to do it is by turning this into an optimization problem. So what we do is we define a cost function, and this cost function contains
a comparison between the field we want, our target, and the field that the SLM produces at a certain point in the iteration. And then we keep iterating in such a way that we minimize this cost. And when the cost is minimized, we're going to be as close as possible to our target. So this minimization problem is quite interesting because there are a lot of parameters. Each SLM pixel here, and there will be hundreds times hundreds. Each SLM pixel is a free parameter that you can change, optimize the result. So we need an efficient optimization routine, and we use conjugate gradient minimization to minimize this cost function. So more details are on this paper, and this works quite well. We can design optical traps like this, for instance, that are very accurate, down to a few percentage of error compared to the target. So these optical traps can be quite accurate to the point that it is possible for us to design trapping potentials in which we can control the position of each individual energy level in that potential. And so one thing we can do, for instance, as you will see, we are interested in number theory, so how about the prime numbers? This is a potential where we have 15 energy levels, and these 15 energy levels are equal to the first 15 prime numbers. And in our implementation, these energy levels are on the longitudinal direction of the guide, of the atom guide that you saw in the previous slide. So we control the profile of the light along the longitudinal direction, and we can fit all these energy levels in the potential. So this is what we've done experimentally with the spatial light modulator. We have not put atoms yet in the potentials, but we have realized the potentials with the spatial light modulator. But before we do this, we need to step back a moment, because the first thing you need to do ahead of doing the experiment is to calculate theoretically the potential that has those energy levels. And this is again a problem, because quantum mechanics we are used to starting with the potential and calculating the energy levels by solving a Schrödinger equation. But here we want to do the other way around. We start from the energy levels, and we want to calculate what potential has those energy levels. So that's what we can do. There are a number of ways of doing it. And the way we do it is by using a recursive method. Basically, what we're doing is we build this potential one level at a time. We start with just one energy level, which is actually the top prime. So prime number 15 in this case. We start from the potential with just one energy level, and then we build one by one. We go down and we build a sequence of potentials. Each of them have one additional energy levels down to the very final potential, which is the one that you see. So it's a recursive approach based on, as you can see, chain of Hamiltonians. And this is a method that comes from supersymmetric quantum mechanics. And in our paper with Giuseppe D'Andrea, you can see the details. So this is one way of calculating our potential. And this is a small detail, but it's useful to introduce it. This is, of course, all done in dimensionless units. Here we put h equals 1, atomic mass equal to 1, so that our energy levels are pure dimensionless numbers. When we get to do the experiment, of course, we deal with real energy, physical energies. So there's always going to be for us experimental conversion factor between our physical energies and the prime numbers. So experimentally, what we make is a spectrum whose energies are proportional to the prime numbers. There is always a proportionality factor. So from theory to experiment, here there are two examples. In this potential, there are the first 10 primes. In this potential, there are the first 15 primes. And these two images here are the experimental intensity profiles
produced with the specialized modulator. So you can see here there is a physical scale, 50 microns. This is going to be important for us because it is determined by the diffraction limit of our system that we use to project the light onto the atoms. So, for instance, this 50 microns here means that the individual lobes in this intensity profile is only slightly above the diffraction limit of the optical system, which in this case is about 10 microns. We didn't really push the resolution of our imaging system here, so our potentials are quite large. If we implement this with atoms, this is going to be implemented with red, the tuned light. So wherever you see a maximum of intensity is going to be a minimum of the trapping potential. So here you see the lobes of light corresponding to the minimum of the potential. And here you can see the comparison between theory and experiment. The two curves, these two curves here, look quite close to each other, and similar also for this one. We are within a few percent, 5 to 10% discrepancy between theory and experiment. And what we have done here is we have rescaled the experimental profiles and experimental potentials to be in the same dimensionless units as the theoretical potential, so that we can extract the energy levels in dimensionless units, which are in fact the prime numbers. So here you can see that for this potential here, B10, these are our experimental energy levels, and you can see that they're quite close to the corresponding prime numbers. In each case, we are, if you were to round up these numbers to the nearest integer, you get the prime. So that's what we've done. Okay. So now, one comment on this conversion factor between the dimensionless energy levels and the physical energy levels. This is the conversion factor. So capital E is the physical energy levels, little e are the prime numbers. And the conversion factor depends on the atomic mass and on the ratio of the physical, of the length scales of the potentials. Big L is the length of the potential in physical units. So here will be a few hundred microns, and the little l is the size of the potential in dimensionless units. And here you can see that because big L, the physical size of the potential, is limited by the diffraction limit, we cannot make it arbitrarily small. We have to keep into account the diffraction limit. This is really what determines the conversion factor and therefore the energies we are dealing with. And if you put in the numbers for this potential, for instance, we get potential depths of the order of tens of picokelvin, which of course are incredibly cold. And this means that all these energy levels are also very close together. So if we want to do any dynamics of moving atoms across energy levels, this will be very long time scales as a result. So this will be a challenge. However, as I said, in this experimental realization, we didn't really push the resolution of the imaging, the resolution of the optical system. If we were to do this in a quantum gas microscope, the diffraction limit could easily go down to a micron, and the time scales and the energy scales will be completely different. Then the energies will go up by a large factor, and we reach from picokelvin, we go back to nanokelvin, which is more doable. So these are the kind of experimental challenges when we get to put atoms in this. So having done the prime numbers, we also looked at different sequences. This is the potential for the first 10 lucky numbers. Lucky numbers are a different sequence of numbers in number theory. Lucky numbers they're similar to prime numbers. They share some of the properties of prime numbers, but they're different because they're obtained with a different sieve than the sieve that you use to calculate prime numbers. So this is just an example of the versatility of the approach. Really, any finite sequence of numbers that we may want to do, we can calculate potential and implement it with a specialized modulator. So it is a general technique. So in our lab, we use a phase-only specialized modulator, but
in recent years, there have been so many experiments that use different light sculpting techniques, like digital micromirror devices or fast scanning acoustic optic deflectors. And if you look into these alternative techniques, you'll find that they are all equally good to produce these kind of potentials. So many groups can work on this. You can use a DMV, and you will face the same degree of complexity, so to speak, as what we have to do with the spatial light modulator. So all these methods are I think they're quite similar when it comes to doing this kind of experiments. In particular, here in this work, in the group of Jörg Schmidtmeyer, they precisely designed an intensity profile, which in this case was meant to compensate the corrugation of an atom chip trap, so that the result would be this very nice flat potential for the atoms. This is the atom chip trap. This is the intensity profile that's meant to compensate for it. So this, of course, was done in a different context, but it's just an example to show that it can be done, and this was done with the DMV. So it's very similar to what we're doing. So in terms of general motivation, why do we do this? So we're very much inspired by the linkages between quantum physics and number theory. Number theory is a very fascinating branch of mathematics. There are so many unsolved problems in number theory, like the distribution of primes, the Goldbach conjecture. I'll get back to this later on. How to factorize numbers. And over many years, there have been interest in linking this to quantum physics. So can quantum physics provide a different perspective to address these problems of number theory? And one early example of this is the Polya-Hilbert conjecture that connects quantum physics to the problem of the non-trivial zero, but of the zeta function. So there is a very good review of this perspective in this article here. So what is our approach? Our approach is, given that we can design these potentials with an assigned spectrum, so we can choose the energy levels, then we start from a sequence of numbers, and we see these numbers as the energy levels of a quantum system. And once we have this quantum system, we can imagine that we can put atoms in this system, and then we can move the atoms across these energy levels, and we can do mathematical operations by moving the atoms between energy levels. So this idea is a kind of quantum abacus. So how we would do this? Let's say that we start from the ground state. We start from atoms in the ground state, and then to populate specific energy levels, we can apply a resonant time-dependent perturbation. We also have a collaboration with Carrie, who is an expert of quantum control techniques, and he's very promising to perform these kind of operations, but on a faster, more optimized timescales compared to just a simple harmonic perturbation. And there is a paper coming out. This paper is in preparation, where we explore all of these ideas. So this is the way we can manipulate atoms. We can perform operations by manipulating atoms inside this potential. And so this is the general overview. For the rest of the talk, I would like to talk specifically about how we can use these potentials to do prime factorization of integers. And there are many ideas on this, and then we also have this has already been done with cold atoms in the Russell group in collaboration with Wolkenschlag. So this was an experiment where an atomic interferometer was used to factorize integers. But there are other ways of doing it, and in particular, Wolfgang has worked on this problem a lot. And And the most recent paper along these lines is by Giuseppe and Andrea. In our approach, in the simulations that I'm going to show next, we are very much based on this paper by Valentin. So now this paper is the factorization of semi-primes. So these are integers that are just the product of just two prime factors. And so that's what we're starting from. Giuseppe and Andrea's paper then provides an algorithm, a proposal of an algorithm that can factorize any integer, not just semi-primes. But for the rest of the talk, I will concentrate on this, and I will show you simulations that give us an idea of what we could do in practice in an experiment to actually implement this. So that's the plan for the rest of the talk. So we need, to do this, we need not a one-dimensional potential like shown until now, but a two-dimensional potential. You can do that with the spatial light modulator. We haven't done it yet, but I think it's doable. The spatial light modulator, of course, can program the light on the whole plane, so we can also produce two-dimensional potentials. And what we need here for this factorization algorithm is a two-dimensional potential that is defined like this. So it is the same potential along x and along y, and it's the sum of the two potentials. And these potentials are defined like this. They are the logarithms of the prime numbers. So until now, I showed you a potential that had the prime numbers as energy levels, but for this, we need the logarithms of the prime numbers. So we have the same potential. So for instance, here we have the first 10 primes, the logarithms of the first 10 primes. So that's what the potential looks like. And if you do the 2D version of this potential, this is what it looks like. So you have the same potential along x and along y. It's the sum. So this is a separable problem. And the wave functions in the 2D potential are going to be the product of the wave functions in the 1D potentials, and the energy levels are going to be the sum of the energy levels in the 1D potential. And this shows us how we can use these to factorize a number. So let's say we want to factorize semi prime n, and we want to find the two factors p and q. The way to do it is to prepare the atoms in the energy levels of the 2D potential, which is equal to log n. And because n is p times q, then log n is log p plus log q. And this means that in the 2D potential, this is the state we're going to prepare. So this is the most general state in the 2D potential that has energy log n. And you see, we have degeneracy here because you can have an energy log n by having energy log p along x and energy log q along y, or energy log q along x and energy log p along y. So these two states have the same energy. So in general, we have degeneracy. So by exciting the atoms onto this energy level, in general, you're going to have a superposition of the two. So this is the preparation stage. We want to create a state. We can do that with, for instance, with resonant time-dependent perturbation starting from the ground state. And then comes the readout stage, which is taking an image of the state that we have created, looking at the density profile of the cloud. And from the density profile of the cloud, you can extract the two factors, P and Q. So let's look at a very simple example to see the idea of this. So for instance, let's say that we want to factorize 6. And for this, we only need a potential here that only contains two prime numbers, so log 2 and log 3. And these are the energy levels of the 2D potential. And this is our target state. So we apply a perturbation that is equal the perturbation boost frequency is equal to log 6, and we're going to populate these states. Now, if you look at these two states individually, we have the density profiles that look like this and this. And here you can see immediately how to extract the factors. Because all you have to do is to take a crosscut along this direction, and you're going to find a node here. This tells you that this state has energy log 2 along x. And this is a node because log 2 is the first excited state, which has just one node. If we do the crosscut along the other direction, we see two nodes. And that's because along the y direction, the energy is log 3. So it's this state here, which is second excited, and we're going to see two nodes. So this is how you extract the factors. You can just look at this and count the number of nodes. And similarly, for this case, x and y inverted. Now, in general, as we saw, there's going to be superposition of the two. The situation will be a little bit more complicated, but there are situations where it is actually possible to just populate one of the two. And in those situations, that's really advantageous, because then you're going to apply the perturbation, but you're going to populate only one of the two, and the readout is the simplest possible case. So the way to do this is by playing with parity. So parity with respect to x and parity with respect to y. So our states have well-defined parity along x and along y. So for instance, log 2 is an odd state and log 3 is an even state. So one thing we can do here, for example, is to use a perturbation that has this form. Now, this is the special part of the perturbation x squared y. This is not the most practical perturbation to do in the lab, but it's just for the example. And so let's see what happens. This perturbation has a well-defined parity along x and along y. It's even along x and it's odd along y, which means that if you go look at the matrix element of the perturbation with state log 3, log 2, which is this one here, the matrix element will be non-vanishing. And the matrix element with the other state, log 2, log 3, so this one here, will vanish due to selection below parity. And this means that in this example, if we choose our perturbation judiciously, it is indeed possible to populate just one of two states and avoid superpositions. Now, this doesn't work all the time. It only works if the two states involved have opposite parity. So for instance, this one is odd, this one is even, then all this is going to work. If the two states have the same parity, we will see an example in a moment, then this is not going to work anymore, because if the two states have the same parity, then what happens is that also this matrix element vanishes, and you apply your perturbation, but you will never populate an excited state. So this works, but not every time. So when it does not work, then we do need to deal with superpositions. And this is, for instance, an example of factorizing 10 to 2 times 5. So here the two factors, log 2 and log 5, correspond to states that have the same parity. So we're going to deal with the superposition of these two states. And then this is the superposition that you can achieve. And this superposition here is a 50-50 superposition of this and this. And it turns out that this is the easiest thing to do in this situation. And the way to do it is by choosing a perturbation now, which is invariant under exchange of x and y. If you choose a perturbation of this form, then you will populate, then you will create a 50-50 superposition of the two excited states. And this is the result. So as you can see, the situation is a little bit more complicated. It doesn't look very complicated here, but it gets more and more complicated if you increase the numbers and you go towards larger and larger times. So the wave function here in the center can look increasingly complicated, but there is a way we can still extract the factors. And the way to extract the factors is to look at the wave function off center. So for instance, here, if we do a cut off center along this direction, I see one node. And this one node tells us that log 2 is one of the levels, is the first excited, and therefore 2 is one of the two factors. And the reason why this works is that if you look at this region here of the wave function, this region here is dominated in this superposition here, this region here, as the contribution of this wave function here. And this contribution here, see, this wave function is elongated. It's elongated because it's elongated along x because the larger factor is the energy along x. And therefore, if I look at the crosscut perpendicularly, that's going to be this is going to be the smaller factor in this wave function. And therefore, if I look here, that's what I'm going to find. I'm going to find the smaller factor. So out of the two factors, out of the two prime factors, I'm going to find the smaller factor. So the smaller prime. So this is a way to, this is a possible experimental approach to this. All you need is a perturbation that is invariant under the exchange of x and y. For instance, Wolfgang in his proposal suggested the delta function along the diagonal, so delta of x minus y. This would work, or you could use an x times y, similar to what I had in the previous slide. So therefore, to conclude this investigation, what would you do in an experiment? First of all, it's worth trying a perturbation that has opposite parity along x and y for the chance of populating just one excited state. Failing that, then your best bet is to populate a 50-50 superposition of the two states, for which you need to use a perturbation that is invariant under the exchange of x and y. Now, of course, we want to go towards larger and larger numbers. We're not happy with just 6 or 15 or 10. And so one challenge here is that to go towards larger numbers, then we need to produce potentials that have more and more energy levels. Now, if you increase the number of energy levels in your potentials, you're going to end up with potentials that are more and more complicated. They contain more and more of these wiggles. I should emphasize that these wiggles are not regular. They're not like superimposed optical lattice. They have an irregularity. And this irregularity comes from the fact that prime numbers are irregular. They are irregular space. And this gives you a potential that has these irregular wiggles. And you already saw that in the prime number potential at the beginning of the talk. So it's a challenge to put more and more energy levels in these potentials, but we want to go beyond 10. So what is the approach here? The approach is to try to be as economical as possible with energy levels. Don't put more energy levels than strictly necessary. For instance, in this case, we have the same primes along x as along y. That's a bit redundant. It's not always necessary. So, for instance, what we can do, this is an idea that Enzo had recently, is instead of having the same primes along x and along y, let's put some of the primes along x and some of the other primes along y. So that we end up with two different potentials along x and y, but this way we can represent more primes in our potential. So for instance here, so therefore we call this the alternative potential because what we do is we alternate the primes. So these primes in this group that we can call alpha are along x and the other primes are along y. This is group beta. And you see we alternate. So this is here, this is here, this is here, this is here, and so on and so forth. So it's the alternative potential. Along x and y, we now have two different potentials because they have different energy levels. And we can combine them by summing them so that we obtain this 2D potential, which also looks a little bit smoother compared to the potentials that we had before. So this is good from the experimental point of view. And as you can see now, we can go up to 71. So we managed to put twice as many primes now potentially. So we do the same approach of populating our excited state with a frequency omega equal to the logarithm of the prime, the logarithm of the number we want to factorize. And here we see an additional advantage of this, that because the two potentials are different along x and along y, this excited state is there is no longer degeneracy. So there's just one state in the 2D potential that has this energy. So we no longer deal with degeneracy. So the preparation stage is to populate this potential, and the detection stage is to take an image of the wave function, where again we can count the nodes along x and along y and determine the factors. So for instance, here, if I look along x, I see 3 nodes. And this tells me that along x, we are in the third excited state, and the third excited state in the Vx potential is logarithm of 11. So we have determined one of the 2 factors. And then you can do the crosscut along the other axis, and you can find the other prime factor. Of course, this only works 50% of the times. The assumption here was that out of the 2 factors that you have in the number that you want to factorize, the requirement is that one of the factors is in this potential along y, and the other one is in this potential along x. This doesn't always happen, only happens a lot of the times. If you're not in this lucky situation, what do you do? This is work in progress. There is a number of things one can do. Maybe in the interest of time, we can discuss after the talk. And finally, we can simulate the dynamics. So if we apply a resonant perturbation at the required frequency to excite our excited state, we're going to see rapid oscillations. And this is what we find. So for instance, if we were to factorize 2881, we can populate this state, and we apply time-dependent perturbation, and we just follow the radio oscillations. So the transfer time is here at the peak of the radio oscillation, where we can see that we have a pretty good population of this state. The ground state has gone to almost 0, and all the other states in the potential have negligible population. These are what the simulations look like. This is the excited state that we want to populate, so this is our target state. And here is how the state evolves as a function of time. So for instance, if you place yourself at the best possible time, where your population is maximum, this is what it looks like. So you still see a little bit of the ground state, but definitely this wave function is visible. So you can count the nodes in this wave function. And if you are a little bit off from the best possible time, like here and here, you can still do it. So there is a poster on this on Thursday. Valentin is presenting a poster. And another thing that is worth mentioning, which is useful, is so you have to ask the question: when you switch on the population and you want to populate this excited state, is the transfer time dependent on the state you want to? Is the transfer time dependent on the number that you want to factorize? In which case, you really have to probe a lot of different evolution times to actually find the best time. It turns out that depending on the choice of perturbation that you have, the transfer time is actually similar for many different numbers that you want to factorize. So this is a really nice thing. It's an advantage from the experimental perspective that the transfer time is almost it's quite comparable. It's quite independent of the number that you want to factorize. So all this will be in Ranzo's poster. So I suggest that you go and look at it on Thursday. So do I have I think that's probably enough time. So I suggest that I finish here. So thank you very much.
My question is, how do you prepare the data start out from the ground state?
So we start from the ground state and we apply it's an additional. So, for instance, if my perturbation was it's with an additional field. So, for instance, if I was to apply a perturbation which is delta of x minus y, which experimentally, of course, would be a smoothed out version of that, then you apply an additional field. It could be an additional optimal field. We are not thinking about interactions here. So the ideal case scenario here is to have enough atoms to take images, but those that would have to be a non-interacting condensate. So we could have some interaction with resonance, or we could have a sufficiently dynamic sample. The interactions are not important. But I think really we would have to use a flashback resonance to cancel out the interaction. So because what we just see here is really single atom groups. Interactions will be used to model. If you have interactions, we can take them into account directly. But of course, with interactions also comes thermalization. And of course, in this situation, you don't want. You want to minimize thermalization. Just to give a quick example, this transfer time for typical physical parameters would be of the order of 10 seconds. So it's a long transfer time because energy states are really small and therefore time states are really long. So that's a challenge. We need to avoid dissipation and thermalization, at least for the 10 seconds that it takes us to. So those are all part of the challenges. Yeah. We need to think about that. But yes, we need to think about that. It's a good question, but most of the parameters can be completely so yeah, we need to think about that. Just for the clean situation of starting from the ground state. And if you have so just from the perspective of modeling a simple case, you start from the ground state, so and then you just apply a single frequency perturbation. Your set will be? Yeah, yes. And this will be part of future work where it's with a real PC, how that spectrum changes and what you can do with it. Yeah, that's all part of future investigation. Yeah.